Hello. I'm going to try to explain here where temperature comes from. And essentially it's based on applying statistics to Newton's laws of motion. So drawn right here I have a box. And we're going to assume we have a cubic box, side L. And you can even consider that the area of a side of this box, A, is just L squared. And the volume of the whole box is L cubed. So this makes it easier. It's actually a little easier to deal with than a sphere. We have flat surfaces. Inside this box, we have a gas. And we're going to consider a gas as just a bunch of particles that are moving around in random directions, bouncing off of each other and the walls of the box. And this is a big deal. In the 19th century, a lot of physicists and chemists didn't consider that a gas was really made up of particles. There were other explanations for what matter was at the fundamental level. You can look up the debate between atomists and realists. But we're going to be atomists here and assume that a gas is made up of a bunch of really tiny particles. And we're going to assume that these particles follow a set of rules. These rules are called the kinetic molecular theory, sometimes kinetic theory for short. So the postulates of kinetic molecular theory, I'll move over here, see if I shrink this up to fit the whole screen. We have a large number of particles, capital N, for a big number, and each one is mass m. We'll assume they're all the same particle, so assume what we call identical particles. They're moving at random speeds in random directions. The particles are much farther apart than their individual sizes. We'll assume that they're point particles. The particles obey Newton's laws of motion. F equals ma, Newton's third law, the action-reaction law. And they exert no action at a distance forces on each other, which means there's no gravitational concerns, magnetic or electric concerns. The only way they can exert forces is by colliding. And then each collision between particles and the walls are elastic. There's no energy lost. Last rule, you can assume all potential energy is zero. But this actually goes into the whole no distance, action at distance forces. But we'll also assume that there's no net gravitational force downwards, that if we put one particle in this box and it's stationary, it's not going to go anywhere. There's no net acceleration downwards. We're going to ignore that. Part is because these particles are incredibly tiny and low mass, so that a gravitational force on them, their weight would be really small. Another way we call, another description, or name for this description, is these are the ideal gas rules. So we are describing an ideal gas, an idealized gas. And for the most part, this actually holds up well to lots of measurements and explains all of our relationships between pressure, volume, and temperature. So let's go back to our box. And I'm actually going to look at, let's pretend we have a single particle in the box, because we have to think about one particle first. And that one particle is going to collide with the wall and bounce off. So we'll look at a side view. It's going to hit the wall and bounce off. And in many ways, there are different components to this particle's velocity. The y component of this particle's velocity, we consider like this is the plus y direction, and this is the minus y direction, stays the same. It's going to hit the wall and then bounce at an angle and continue going up. So the change, my screen moved. The change in y momentum, which would be m delta vy, is 0. But there is a change in x momentum in this case, which is m delta vx. In this change, this particle, the final momentum here, is actually m vx, because it's moving in the positive direction, and we're going to subtract out its original momentum, m minus mvx, I'm moving off the side of the screen there. And that is equal then to 2 mvx. So the wall actually flips the momentum of the particle, but that's really sort of a change in twice the initial momentum of the particle. It's a strange way to look at it. And this is again, of course, considering that that's Vx originally, and of course that's Vy. So when it hits the wall, the Vx gets flipped, but the Vy stays the same. Now, this particle is going to exert a force on the wall. The wall is exerting a force on the particle. It's changing the x component of the particle's velocity. It's accelerating the particle, changing the velocity. So force, remember, we can look at as change in momentum over change in time. So this is the force that the particle exerts on the wall, which is the same magnitude as the force that the wall exerts on the particle, which is equal to mvx times 2 over delta t. Now, let's consider this particle keeps bouncing back and forth off all the walls, and it's going to keep hitting this side wall we've drawn, and it's going to keep doing it back again, back and over again. And so we can consider that the time interval that passes between this momentum change is based on the velocity of the particle. So Vx, let's say it'll go from one side of the box to the other and back, so that's 2L, and the time is delta t. So we can rewrite that as delta t equals 2L over Vx. So now I can consider the whole momentum change on the wall in a particular time interval due to the single particle. So what is the force that this particle exerts on the wall? We can rewrite it as F equals m 2mvx over delta t, which then becomes 2mvx over 2L over Vx, which is mvx squared over L. And hopefully you're looking at that going, hey, that kind of looks like a kinetic energy statement. Now, that's if we have just one particle in the box. But say we have n particles, a total of n particles, and they're all exerting forces on the wall. They all have different speeds, but we're going to assume their masses are all the same. So the total force, so this is a single particle, the total force due to all particles will be m over L times Vx1 squared plus Vx2 squared plus all the way to Vxn squared. Every one of them has an associated m over L times its speed squared, and that's the total force all particles are exerting on one of the walls. So I can pull out that m over L, and it's really just the sum of the squares of the velocities. We can consider that there is some average velocity. So Vx squared average of all of them is the sum of all the squares of the speeds over capital N, the total number of particles. Again, this is going to take into account that some particles are slower and some are faster, so we're just going to look at the average of all these particles to get the average force that gets exerted on the wall. Because if I take that n and multiply it up here, that's the same as the sum of all my square of my speeds. So the force that's exerted on the wall due to all particles can be written as m over L times n times Vx squared average. Because this piece here is exactly the same as that piece there. So that is the sum of all the forces, all the particles hitting one of the walls of the box. We also know that the particles can be moving in one of three directions. So we consider the three-dimensional Pythagorean theorem, and we can assume that the average speed is the average speed squared is the sum of all the individual component averages. But since this is random, and we could flip our cubical box any which direction, because remember, it's just a cube, and I picked one side of it, I could rotate this. It doesn't really matter which side. That's all arbitrary. So I could say that the average of the square of all the speeds is just 3 times the average of the square of the x component of all the velocities. So I can substitute this back into the all particle force equation. So the force on all due to all particles, the net force due to all particles in the box on that wall is actually equal then to m over L times n times the average of the square of all the speeds over 3. So that's essentially saying that the net force is distributed over 3 directions. That's where that dividing by 3 comes from. Pressure is force over area. So there's some pressure in this box due to all the particles. I can get rid of force and write this in terms of pressure and actually volume. So the force is m over L times n times v squared bar. It's the average of the square of all the velocities over 3. And it's this whole thing divided by a. Now, when we write it this way, we can just bring that L down there, and we can move that down there, that 3 down there as well. But what is the area of one side of this box times L? That's just the volume of the box. So now what I have is that the pressure is equal to 1/3 times the total number of particles times m times the average of the square of the speeds over v. This is starting to look hopefully very familiar, because I could turn this into pressure times volume is 1/3 times the total number of particles times m times the average of the square of the speeds. So the pressure times the volume is constant. If the number of particles stays the same and the average mass, or the mass of each particle is identical, and then that's considering the average of the speeds. But how could the average of the square of the speeds actually change? This is where we get a definition of temperature. So what we saw earlier in some videos is that the pressure times the volume of a particular gas, if it's enclosed in a container of some volume V and at a particular pressure, is proportional to the temperature that is in this box. And so temperature itself is actually then proportional to this 1/3 nmv squared, the average of the square of the speeds. Now, the number of particles is just how many are in there. That's not necessarily something that could, well, that could affect the temperature, but we see something pretty big here, because an mv squared, that's a kinetic energy term. And so we now have this relationship where temperature is proportional to the average, I'm going to write it with these square brackets, of the kinetic energy of the particles. So temperature is a statistic. It is the average kinetic energy of a group of particles.